Hello everybody, this is Dr. Christopher White, and in this video we're going to be looking at how and where does groundwater flow. So when we think about groundwater flow, it's going to be affected by three main variables. The first one is going to be the slope of the water table. The steeper the slope, the faster the groundwater flow will be. The next variable which is going to affect groundwater flow will be the porosity and permeability of the layer or layers of rock through which the groundwater is moving. So obviously, as we've previously discussed, high porosity, high permeability layers of rock will allow for a fast groundwater flow. Low porosity, low permeability rock will produce a much slower groundwater flow. The final variable is the geometry of the layers of rock in the subsurface. So if you imagine you have a situation where you have a nice sequence of rocks, they're all nice and horizontal, there's no deformation, well, in that case, the water will be able to flow along the porous layers of rock relatively easily. If, however, you have a sequence of rocks that have been deformed, so let's say there's a big fold in the middle of your sequence of rocks, that's going to be a problem, because as the layer of rock containing the groundwater approaches the fold, the geometry, the angle and orientation of that piece of rock is going to change, and it may change in such a way that it stops the groundwater flow from going any further, in which case your groundwater flow is stopped. So those are the three variables that are going to affect groundwater flow. So we're going to begin by looking at the geometry of the water table. So we can see we have a diagram over here on the left, and we can see that the subsurface in this case consists of just one material. And this material is clearly highly porous and permeable, so groundwater flow can occur relatively easily. So the first thing that you will notice is that the water table is following the three-dimensional topography of the surface. So you can see over here we have elevated terrain, the water table is elevated. Topographic low over here, the water table is at its lowest. So you can see that the water table is following the topography of the surface. Now it is not a one-to-one match, but it does follow the same general trends which are defined by the surface. Now, where we have areas with elevated terrain, the water table is going to be subdued compared to the topography. So what this means is that the unsaturated zone will be thicker. And so you can see in this case over here where we have the elevated topography, you can see we have an extensive undersaturated zone or unsaturated zone. And so in this area here, we would describe the water table as subdued because the unsaturated zone is so thick. In contrast, when we come down here, we can see the unsaturated zone is tiny, and so we would not refer to that water table as being subdued. Now, the water table and the groundwater below it will follow the topography and flow downhill, because you can see straight away that the geometry of the water table, and more accurately the water table slope, is going from the high ground over here down to the topographic low right here. And so just like water flowing across the surface, the groundwater will do exactly the same thing. It will follow the water table down the slope until it reaches the lowest point. So this downward flow is defined by the slope of our water table, and in this case the slope of our water table is being defined by the topography. Now, in terms of the water table itself, it will typically cut across rock units. However, if it meets an impermeable layer of rock, the water table will obviously have to change its position or stop. So in this case, you can see that the water table is not meeting any impermeable layers of rock, so the flow is not restricted. You will notice that the water table itself, though, is actually coming out onto the surface here, and over here, and down here as well. So in this instance, we have an elevated lake, which is being fed by the groundwater flow. Down here, we obviously have a river, which once again is being fed by the groundwater flow. So the addition of water into the lake, into this elevated lake, and into the river will help to maintain them, will help to supply water for them. Now, When your water table begins to head into an area of horizontal topography, so think of something like a plateau or a relatively flat area of land like a lake or a broad river valley, in that situation, your water table is going to go horizontal like the topography. And in this case, because there's no slope, the groundwater flow is going to slow down significantly, or there's going to be no groundwater flow. So if you want groundwater to move, you need there to be a slope on the water table. As soon as you enter an area where there is no slope on the water table, the groundwater flow will get very slow or come to a complete stop. Now, another thing that you'll notice is here on the diagram, we have these two dashed yellow lines, which are marked as groundwater divides. And so these are just like the divides that separate river valleys. So you will see over here on the right, we have an area of elevated terrain. You can see this is the high point right here, and the terrain is going downhill towards the west, towards the left. Now, you will notice that if you have groundwater located here, it can go one of two ways. It can flow down the water table in this direction, or it can flow down the water table in this direction. And so this is defined as a groundwater divide, and it marks a point where your groundwater can flow in two or more different directions. Just like how you have divides that separate river valleys and the water that flows into the river is contained within its own catchment area. Okay, so the next thing we need to think about is the slope of the water table. So to put it most simply, the steeper the slope, the faster the flow. This isn't particularly surprising. If you think of a river going down a steep slope, it will flow faster than a river going across a gentle slope. So once again, this is the same diagram we were just looking at. You will see that the water table in this area has quite a steep slope following the topography above it. So this is obviously going to drive a groundwater flow down the slope of the water table. Once your water table begins to become more horizontal, the flow will steadily decrease. So groundwater flow is typically measured in cubic meters per day, cubic meters per year, or gallons per day. Now, the rate of flow is primarily controlled by the permeability. How easily can your groundwater, move through your layer of rock? And then, obviously, you also have the steepness of your water table having an effect as well. So if you have, in this case, a sequence where the entire area is underlain just by one layer of rock, so the permeability and the porosity is consistent across the entire diagram, what is going to be driving the groundwater flow? The answer is going to be the slope of the water table. Now, if you had a situation where you had another layer of rock coming in, and this layer of rock was less permeable, well, in that situation, you are going to see a change in the groundwater flow. You're going to see rapid groundwater flow in the more permeable layer, and as soon as the groundwater enters the less permeable layer, you are going to see that groundwater flow slowing down. So permeability is the first control, but there's also an influence from the steepness of the water table, and that is a reflection of the topography. So high permeability layers, such as something like a cavernous limestone, will have high groundwater flows, followed by porous rocks, so sandstones and conglomerates. In terms of shales, they will typically have the lowest groundwater flow, and that's typically because if they aren't compacted, the pores will be quite small, and the permeability will not be as good as something compared to a sandstone. Now, as the water table will follow that surface topography, you will have regions of it that will be steeper in areas where you have steeper topography. And obviously, vice versa, in areas of more horizontal, subdued topography, you will have a more horizontal water table. And so this means that, obviously, water, just like water on the surface, the groundwater will flow downhill under gravity. It will follow the slope of the water table. So the slope of the water table is referred to as the hydraulic gradient. And obviously, the steeper the slope, the higher the gradient. And so the higher the hydraulic gradient, the faster your groundwater will flow, providing there is a layer of rock through which it can flow. So if you assume that all things are equal, steeper water table slopes equals a faster flow. Okay, so now let's think about the type of rock that our groundwater is moving through. So we need to move on to aquifers. So an aquifer is defined as a large body, so laterally extensive, so it extends over a large area of permeable, saturated rock through which groundwater can flow. So what you're looking for is for instance, something like a layer of porous sandstone that extends over, hundreds of kilometers maybe. So obviously, because it's porous and it has a good permeability, groundwater will be able to move through it quite easily. So typically, if you have a material that has abundant large pores or fractures or cavities, they will be the materials that will make the best aquifers. And the extent of the aquifer is limited by impermeable layers or surface topography. So as we've discussed, if the topography becomes gentler and essentially becomes near horizontal, groundwater flow will slow down. If you have a situation where your groundwater flow is impeded by some kind of impermeable layer of rock, like a granite, well, that also is going to affect the ability of your water to move along your aquifer. Now, aquifers come in two kinds. There are unconfined aquifers and confined aquifers. So let's begin by looking at an unconfined aquifer. Now, this is the most common type. They are open to the Earth's surface and they will typically have an impermeable layer beneath them. That's what helps to keep the water actually within the aquifer. So if we look at our diagram here, here is our surface. We have our unsaturated zone here, and then we have our saturated zone here, which is full of groundwater. You will notice that the entire thing is permeable, so the water can move from the surface down towards the water table pretty efficiently. You will also notice that we have groundwater flow moving from left to right, but you'll notice that the groundwater is inhibited from going deeper in the sequence by this layer of impermeable rock right here. So an unconfined aquifer will be open at the top, and it will be essentially confined at its base by this impermeable layer. Now, this means that your unconfined aquifer can be recharged, can be fed by water coming in from further upstream, or water infiltrating down through the unsaturated zone and into the saturated zone. So an unconfined aquifer has two sources of water which will enter it. Now, a confined aquifer is slightly different. So a confined aquifer has impermeable layers above and below it. So we can see that here. Here's our confined aquifer, and it's confined above and below by impermeable materials. Now, in the case of a confined aquifer, the flow of groundwater that is entering it, or the flow of water, should I say, that's entering it, is purely from further upstream. So it's got to come in from another location and flow down through the aquifer here. There's no water coming in from above. It's only from groundwater further up the aquifer. Now, in terms of the low permeability layers, these are referred to as aquitards. And they are layers of rock or sediment that have a very low permeability, or they are impermeable, and so obviously they are going to restrict flow and confine it to within the aquifer. So these two layers of mudstone here would be classified as aquitards. When we think of aquifers, we tend to think of the nice, continuous, relatively horizontal layers of rock that we saw on the previous slide. However, there is another type of aquifer which is referred to as a perched aquifer, and these sit above the broader water table. So if we look at the diagram here, we can see here is our saturated zone, so obviously our water table is right here. However, above our water table, we have these two isolated bodies of porous sediment, which can contain water within the pore spaces. So in terms of these perched aquifers, they form when you have a discontinuous layer of permeable sediment. So discontinuous simply means that the layer doesn't, continue. It just stops and starts. So the layer starts here and stops here. The sediment within it, or rock within it, is permeable. So there's pore spaces into which the water can enter. And it is underlain by an impermeable material. So that water can't escape. And so once the water enters your perched aquifer here, it can't go anywhere because it's stopped from moving downwards by this impermeable layer. It's now confined within this perched aquifer. Now, this means that groundwater will collect within the permeable sediment located above the impermeable rock or sediment. So a good example of this is when you have a buried lake, for instance. So if you imagine that once upon a time this was a lake, well, underneath your lake, you will tend to build up quite a thick layer of clay. But the lake itself will fill up with coarser sediment, let's say sand. And so over time, what you end up with once the lake gets buried by more sediment later on is you have this lens of sandy material underlain by this mudstone. The mudstone is going to act as your aquitard and stop the water from moving downwards, and your sandy material is going to act as your aquifer. It's going to store the water for you. So once we know where the water table is and where the aquifers are located, how do we actually access the water contained within them? Well, in order to do that, we are going to use wells. And wells can either be drilled or dug, and the aim of them is to intersect the water table. And so all the well is it's essentially an artificial void into which water can flow. So the water can leave the aquifer and enter the well, and then obviously it can be removed from the well. In terms of well construction, obviously in past history, it's required teams of people to physically dig the well down and then line it with stone, for instance. And then obviously the groundwater will seep between the stones and fill the well up. More modern examples use drilling rigs, and the drilling rigs will just simply drill a hole straight down to your water table, and then they will line the interior of that hole using something like stainless steel in order to stop the borehole collapsing in on itself. So obviously once you create your well, you're obviously creating a void, and the groundwater will naturally want to flow into it. So the problem that we have with wells is that the ability of the groundwater to move into the well is defined by the height of the water table. So as long as the bottom of your well sits below the water table, you will have water entering your well. However, if the water table drops below the bottom of your well, the flow of water will stop because your well will now be exclusively within the unsaturated zone. And so in that case, your well will obviously be useless. Now, there is a final type of well which we need to talk about. These are referred to as artisanal wells, and or artisan wells, should I say. And these are wells where the pressure, the groundwater flow is so strong that water will actually be forced up the well and out of it. And so in this case, what you have essentially is an artificial spring. And these artisan wells are important because they are used in the production of things like bottled water. Okay, thank you for watching.